Hello, everyone. I wish to go over some questions with you on the review for midterm. First, on the concept part, right? You guys have all the flashcards you needed, but it's really not about memorizing word for word. It's about applying them. It's applying them. For example, the definition of limit for when f of x is approaching a, right? So you look at this intuitive definition of limit. So that notation, so when you see that notation, right, you will be reflecting on what it means in its entirety, including that this means f is defined on some open interval that contains a, except possibly at a itself. As we talk about in class, the limit, when we consider the limit of the function as x approaching a may or may not be in the domain of f. And that make it possible for a lot of situations. So limit concept, and the limit from the right, limit from left, which that's the one-sided limit, right? One-sided limit. And when x up, when limit for infinite, the limit is infinity, or limit at infinity. Okay, so these are different concepts. So when you look at these flashcards, right, you may want to reorganize your flashcard, not just in the order that you are given. You want to put all of these definitions together, okay, as one pile of limits definition. So all of these are defined, right? This is the limit of f is infinity, right? But when x is approaching a, but this is the limit at infinity, right? So let's go over those flashcards. So here, the first one, that's the definition that's right here. That's number 8. One-sided limit, okay? One-sided limit, that's one-sided limit. So the definition over here, in all 3 cases, okay, including A, B, C, D, in all 4 cases, right? It is saying that we can make that this f is defined near A, but may not be at A. Okay, except possibly at A. So these wordings are all there. As we keep going, this is the definition of an infinite limit. Okay, I just find it hard to say that, but this is one of the definition, because this definition is typically used for vertical asymptote, right? So put these cards together, vertical asymptote, right? And the next one, which we talk about a bit later, right? Limit at infinity is when x is approaching infinity, right? So the definitions are here. So you want to put these cards together. You want to put those cards together right here for limit at infinity, right? Limit at infinity. So put these cards together and you compare them and study them, okay? And you look at the homework you've done on these concepts, okay? And of course, algebraic techniques are involved. Otherwise, for a concrete situation, it will be hard for us to determine, right? So these cards, since here we're talking about concept, right? So you want to put these cards together. So so once again, the definition about all of these, 1, 2, 3, 4, 5, you bring those cards together and put them in one place. Number 2, describe several ways in which a limit can fail to exist. Well, for a limit to exist, we have a very important theorem, which we mentioned multiple times, many times, right? Which is this one. If limit exists when x is approaching a, if and only if the limit on the side, the two-sided limit not only exists, but also equal. Okay? So let's write them down to see what is the opposite of it, to see what's the opposite. Okay? So if, you know what, I should write down what I recommend you to do. Okay, for the first one, right? Explain all of these different definitions. Okay. All of these definitions. Wait. I'm going a little too slow. Okay. So all of these definitions limit as x approaching a. A is just a finite number. If you have any question about A, right? Some of you ask, oh, A is not given. So A is not given because A can be any, it can be any number, okay? And L, of course, is a limit, right? So for, this is A, you put these cards together, and there's a B, right? Limit from left, limit from right. Limit from right. Oops. Limit from left. Okay, wait. Negative. Wait. Negative. Okay, from left, from right. And you may not see that very clearly, so I retype it. I should make this a bit larger. Okay, we need more space. So A, B, C, D, okay, D, I'm too slow here, D, okay, as x approaching A, infinite limit. So that a contradictory frame. So this is infinity, D. We also need to understand when the limit is infinite, it doesn't have a limit. Okay, that's what I would like to emphasize. Okay, it's just one form. Okay, so when x is approaching infinity, the limit is out. So we have 5 definitions. You want to bring those cards together, do a comparison, and to know what it means. Okay, and to see what's in common. What's in common? Okay, what's in common? For example, on the one-sided limit, right? So intuitive definition of limit, that's direct substitution, right? One-sided limit for the left, for the left limit is called a left-hand limit as x approaching a from left. If we can make the value of f of x arbitrarily close to L by taking x to be sufficiently close to A with x less than A. There's some pretty good pictures in the textbook when x is approaching A. This is the textbook. Okay, the picture when x is approaching A from left, when x is approaching A from right. Okay, so along with that limit. So let me see if I can take that picture. Okay, so I'm going to take that picture. Okay. And bring them right here. For our assumption. we have the flashcard, we have our questions. Okay, we have our questions. Anyway, so these are the pictures approaching from left, approaching from right. Okay, left limit, right limit. Okay, so bring those cards together. Second, describe several ways in which a limit can fail to exist. Okay, this will be an interesting question because we've done so many homework questions. And now when you review, you're not going back to redo those questions unless you need to, brush your algebraic skill. You want to see those limits, those work you've done, and see from this perspective. Okay, there are cases that limit does not exist, right? So what is from the theorem's perspective, right? This theorem we just talked about. Theorem says if the limit exists, if this limit exists, if and only if, which is equivalent to say, okay, which is equivalent to say, and that if and only if and only if the limit from the left, the limit from the right are both. Okay, so I'm just copy and paste these so I can quickly get to write down that statement. And we analyze. So I always choose to write it down, so I might go a little slower. Well, I am going slower so that I can make my point clear so you can see what's written down. Okay. If and only if the limit from the right and the limit from left both exist and are the same. Okay, so this is if the limit exists. Okay, and what's the opposite? Limit at A does not exist. So this is not true. If this is not true, okay, and that means the if and only if part is not true. So this is not true. So this whole thing is not true. Okay, the whole thing is not true. I'm going to move up just a little bit. Okay, I'm going to move up just a little bit. Not true. So I talk about the logic. Okay, so I want you to see from the light of a simple logic, right? If this does not exist, that means this piece and that piece is not true. And I'm going to assume that this is not true. Okay, so I'm going to choose, this is a statement A, and that's a statement B. Okay, statement A and statement B, A and B is not true. The opposite of it. Okay, we understand logically if A and B, the not of it, the opposite of it, okay, A and B. Okay, I'm teaching you a bit logic. Okay, well, look at this table. Okay. A and B is not true is the same as A is not true. Okay, A is not true. Okay, hold on. A is not true. Or B is not true. B is not true. Okay. Well, A or B, A is not true or B is not true. Okay, so have that logic clear. Let's see how many cases could there be. Okay, cases. Okay, it could be that A or B, okay, statement 1 and statement 2, if there's an or case, if one of them is true, then the whole thing is true. Okay, so it could be that A is not true. So this one, so the first case would be the limit case 1, right? That does not exist. Does not exist. And then we can say this limit does not exist. You follow me? I hope you follow me. If you can demonstrate that this does not exist, and then you can say directly that this does not exist. Okay? Does not exist. Okay, I will show you guys examples and homework we've done. Okay? Now, if and the same situation could happen for left limit. So if this isn't from limit from the left, that does not exist, and then the limit does not exist. So case 2. Case 3, right? Case 3, it could be that both exist, right? Both exist. Both exist, but they're not the same. We've seen plenty of these examples, right? And so that's one case, right? Are there other cases? Both exist. I would say these are 3 major cases. These are 3 major cases. And in terms of that, these limit does not exist. It could be that this goes to the infinity. This could be having infinity limit. Okay, these, if they have infinity limit, then that means it doesn't exist. That limit does not exist. Okay, so this including that this may have infinite limit. The infinite limit is no limit. Okay, I just wish to make that clear. Infinite limit has no limit. Okay, so now we have 3 cases. Let's look at our homework, the homework questions that we have done. Okay, illustrate that. I'm going to bring this up, and you can, we're going to look at our homework questions. Okay, we're going to go back to look at our homework questions. Okay. Week two, we handle those algebraic situations. In fact, all of these limits exist. Okay, all of these limits exist, and then you can infer if these limits exist, then the limit from left and the limit from right are the same. Okay, and so that is the situation that agrees the limit exists, and then limit from left and limit from right both exist. So let me make the font a bit smaller. Okay, all right, so that should be clear enough. All right, so next one, homework number 3, we start to see some interesting situation. We've done this homework, right? You can see at 1, the limit from right and the limit from left. So let's observe the limit from left. when x is approaching 1 from smaller than 1. So that's the limit for x is approaching 1 from smaller than 1. And that's one value. And the other one is another value. We've done this homework, right? So these two, one is equals to 1 and the other one equals to 2. So that limit does not exist. But for 0, however, limit from left and limit from right, they're the same, which is 3. Therefore, that limit exists. Okay, so just to remind you, we've done these homeworks, so this one equals to what? Equals to 1, right? And this piece equals to 2. And that's the third case. Limit from two sides are, they both exist, but not the same. And this one, a limit from both sides are the same, which is equals to 3, right? So we have seen these examples. Okay, when we're approaching, I'm going to put an arrow here in case, right? I didn't forget. It's just I didn't have time to do it. But anyway, so these limit from the sides, right? So we get the third case covered. So let's look at some other situation. Okay. Over here, right? Limit from left, limit from right. So case number 3 again, right? So we've done those homework questions. So you guys can look into those. We've done homework questions, we've even done some quizzes on these situations. Now, how about this one side does not exist, for example? Okay, so in this case, I'm going to bring you the other homework. Okay, for homework number 4, I think is in homework number 4. It's infinite limit, right? For example, we just didn't ask you further questions, right? When x is approaching 5 from larger than 5, right? So I'm going to take this example, right? This is example number 1, right? We have a limit. We've done this. We have a limit. As limit, you just have to look a little further. So x is approaching 5 from larger than 5, right? We definitely did this question. And we have x plus 1 over x minus 5. So in this situation, right, when x is approaching 5 from larger than 5, x minus 5, I will write it down. When x is approaching 5 from larger than 5, x minus 5 is approaching 0, but from larger than 0. So the denominator is approaching 0, but positive. The numerator, of course, approaches a finite number. Numerator x plus 1 approaches 6. So numerator approaching a finite number, denominator approaching 0. So the whole limit, this limit is positive infinity. So this is the situation that the limit from right does not exist. And then what do we say about the limit, right? So now we can say this limit, okay? We're not going to say this as approaching, we're going to remove this plus sign. Okay, this limit does not exist. I hope you understand that. Okay, you see, the limit from one side does not exist. So the limit does not exist. Here, of course, it's being asked in different questions. But if we just go further, to take these axes, some of, a lot of these questions, a lot of these will belong to these two cases. Okay, so we do have these cases. Okay, more cases, right? More cases. And this piece it's also in the third case. Yes, the third case happens a lot because also it requires more work from you to demonstrate limit from left, limit from right. But in the case number one, number two, you don't need to write down so much. But in the, you can see from this example that one-sided limit does not exist, which is infinity, then the limit at that point does not exist. All right. Okay, so I hope that explains it, right? I hope that covers that part. Now let's go back to our review for midterm, and we move down further. Limit law. We have learned so many limit laws, but what is the essence of them all? Okay, excuse me. I encourage you to look at the limit laws. Okay, what are the limit laws? So here are some limit laws. This page, there are 11 of them. Okay, and so these two, and we have two more because because I added those to the flashcards for later, is for limit at infinity. Okay, for limit at infinity, there are also these limit laws. Okay, so you want to bring these cards together. But yes, these are very important, useful properties. And in fact, we use them almost all the time. We have to understand whenever we use these limit laws, we have to check, okay, the individual limit exists beforehand. Before you apply the law, you have to check the individual limits exist. If there are 5 individual limits, then you have to check every one of the 5 exists. Okay, so that's mostly important. So once you know they exist and doesn't cause 0 denominator, then you can use them. You can take nth power, and you can take roots as you wish. Okay, so you want to bring these 4 cards of limit law together, or you can just condense it into one, just to make sure you understand that. Okay, always make sure and you check those conditions. Okay, and I talk about that whether you check that condition or not is reflected on your work. Is reflecting your work. So when you apply these laws, any one of the term that you apply the law to, it does not have limit, then that means you're making a mistake. You cannot apply that limit law. Okay. But this is on concept part, so I don't want to make it too long. Okay. Number 4, squeeze theorem. Well, squeeze theorem is a very important theorem, needless to say. Okay. Which is in the neighborhood of squeeze theorem. We have another theorem, right, which is this one, right, which the proof of squeeze theorem used. So this is the squeeze theorem. So for squeeze theorem, when you read these theorems, you must dissect to know what is the condition and what is the conclusion. Only when all the conditions are satisfied, then you can apply the conclusion. Okay, that's what a theorem is all about. So let's dissect squeeze theorem. Okay, so let's dissect squeeze theorem. I should write down something, right? I should write down something for number 3, right? Make sure every individual limit exists every individual limit exists before applying the limit law. Okay, limit law, sorry. Limit law, sorry about that. How did that? Limit laws. Make sure every individual limit involved exists before applying the limit law. Okay. All right. Number 4, squeeze theorem. Okay, so we're going to dissect squeeze theorem. What's in squeeze theorem? Right. So when you see that theorem, you want to you're going to apply it. Right. So the first condition. Right? So I'm going to separate it. Okay. A is that f of x less than or equals to g of x. So the function that's in squeeze in between two other functions. So this squeezed situation needs to be true, right? We need to have a squeezed situation. But this squeezed situation needs to happen near A, except possibly at A. You can see the, it resonates the definitional limit. It resonates the definitional limit, right? So you want to take that to your mind, right? When X is near A, right? Except possibly at A, right? So all three functions don't have to be defined at A. But if one of them defined at A, no problem. Okay, if two of them defined at A, no problem. Three of them defined at A, no problem. If none of them defined at A, no problem. That's what it says, okay? So when X is near A, then except possibly at A. As we chew on these words, we understand the implication, right? We understand. So that's the first condition. Second condition is that there are two individual limits. Okay, there are two individual limits must exist and are the same. Okay, so X is approaching A, right? F of X, so the function on top and the function in the bottom, right? The one in the bottom and the one on the top. There's something in squeeze in between. So the one on the top, one on the bottom, okay? They have, not only they both have limits. So this limit exists, and they are the same. And they are the same. We call the same limit L. So how many condition is that? How many condition is that? 1, 2, 3. So B really implies 3 conditions. Okay, this limit exists, that limit exists, and they are the same. Under these two major conditions, right? The second condition can be written into 3 smaller conditions. And then we have a conclusion. That conclusion is that the limit, the function that's squeezing between is also going to be the same limit, right? So that's the 3 conditions. We have made, so actually we have some interesting, we have some, squeeze theorem. There's some interesting pictures here, right? There's some pictures here, right? This is a very good picture here, right? And what I'm gonna do is I'm gonna copy and paste. I think I might have included somewhere. Okay. Okay. I'll put it on the flashcard. Okay, put it on the flashcard. The squeeze the situation. You just need to remember there's one above, there's one below, but it don't have to be everywhere above or below. It's just in a small neighborhood of it. It's above and below. And none of the three functions have to be, has to be defined at A, which is consistent with the definition of limit. Okay, which is consistent with the definition of limit. All right, so without further ado, okay, and of course here we're reviewing these concepts, but I also wish to point out, okay, that we have given you the tools of applying squeeze theorem. Okay, we'll have to give you the tool to apply squeeze theorem. For example, for squeeze theorem, we made how to apply squeeze theorem. There's a lesson here. There was a lesson here if you wish to see some examples. Okay, and I also wish to remind you, if x is in squeeze theorem, if x is approaching infinity, right? If x is approaching infinity, there's also a squeeze theorem. So I'm going to write down that narrative. Okay, so there could be another version. Okay, so if the squeeze theorem goes like this, right? It's approaching infinity. And the infinity, that will also make a squeeze theorem. Okay, and these examples, I went over them in one of the limit at infinity. Okay, you can see those examples, and I use the squeeze theorem to find the limit. So there are two versions of squeeze theorem. Whether it's approaching A or at infinity, you can also apply squeeze theorem. In the latter case, it's just the definition of limit at infinity would apply, which is you have an interval, right? If approaching positive infinity, it could also be approaching negative infinity. It's just there's an interval that in the positive infinity case, the interval is going to be, from A to infinity, right? As I'm saying this, I want to quote to you, right? I wish to quote to you the definition of limit at infinity. Okay, so I'm going to bring this up. Let's see if you can see it. There you do. Okay, limit at infinity, right? Limit at infinity. No, not here. It should be somewhere here. There. Okay, limit at infinity. Right, so in that case, limit at infinity, right? What does it say? The setting is that there's some interval from A to infinity. A is large. How large? Sufficiently large. Okay. If you go back to some of those lessons, I've made a special point for that. So that's what I meant. So if it's for negative infinity, we can have a version number 3. But I think at this point you got it. You don't really need that version number 3. But I'm going to put a version number 3 here anyway. Right? Squeeze theorem. Squeeze theorem works for situation that you have a squeezed situation. Okay, one on top, one on bottom, and the top and the bottom both have limit, and the limit are the same. So squeeze theorem has 3 versions, and use them as you need. Use them as you need. Okay. And you can also find squeeze theorem used in limit at infinity in my lessons, in the lessons right here. Let me see if you can see that. Yes, you can see that, right? All right. Let's see. Let's go back to review for midterm, okay, on the concept. Okay. What does it mean to say that the line axis A is a vertical asymptote of the curve, draw a curve to illustrate the various possibilities? What does it mean to say that the line y equals L is a horizontal asymptote of the curve? Y equals f of x, draw a curve to illustrate the various possibilities. Okay, the first question, it will be related to vertical asymptote. So you want to put these vertical asymptote and horizontal asymptote, these two cards together. Okay, I highly recommend that. Okay, vertical asymptote. So this is a vertical asymptote. You have vertical asymptote cards, right? And you have horizontal asymptote cards. So let's see, where is it? Limit at infinity. There, right? Limit at infinity and horizontal asymptote. So you have vertical asymptote and a horizontal asymptote. And these two, you put these two cards together. Okay, shuffle your card. Okay, put these two cards together. So how many examples out there? Lots of examples, right? So let's look at a vertical asymptote. Vertical asymptote. If you read the textbook, any textbook would give you a lot of stuff. Okay, they will give you lots of stuff. Vertical asymptote, right? Here. That's 2.1. Vertical asymptote, that's the vertical asymptote, right? These are vertical asymptotes. Okay, these are vertical asymptotes. Vertical asymptotes. And there's a definition of vertical asymptotes over here. That's in the textbook. There, that's the definition. So you have all these different cases. Okay, so let me just make just copy and paste these pictures and put it on your flashcard. Okay, I'll send you another flashcard. I'm going to do some shuffling for the flashcards before I send it to you. Okay, so vertical asymptotes, I put it here, right? There's all these different cases. Right? And in any one of these cases, limit does not exist at A. Okay, as we mentioned that earlier. Limit laws, I'll do that later. Before I send them to you. And horizontal asymptote, limit at infinity. Right, limit at infinity. You can see we study in class, in the lessons we've been studying vertically. Now we're studying horizontally, right? So horizontal asymptote. Where's the limit at infinity? There, limit at infinity. Where are they? Let me find you the definition. You have that definition, by the way. You actually do have the definition. You have the definition. Oh, it's 2.6. I'm sorry. 2.6. Limit at infinity, right? Horizontal asymptote, right? Lots of examples, right? Lots of examples. There we go. So I'm going to put those. In the picture. Okay. Horizontal asymptote, right? That case or the other case. Okay, so that's the horizontal asymptote. Here's horizontal asymptote. Horizontal asymptote. Here we go. Horizontal asymptote. So I'm going to put this next to it. Okay, horizontal asymptote. So you have that, right? So you have that. Let's see. Actually, it doesn't look so amazing. I should take the picture separately. Okay, so hold on. I'm gonna do this separately. Okay, number one. I'll put it here. I'm going to remove this piece. Number two. Copy, paste. So now we have vertical asymptote, horizontal asymptote all together. Okay. And as I recommend you guys just to shuffle your cards, okay, this way as you study. And you don't have to, right? You don't have to, but I just recommend, right? That's how you study, because when you study and review, you start to summarize. You bring things that are similar together. So this will enhance the learning. And you, of course, you also study your examples, right? So this piece, I'm going to bring it all the way with my vertical asymptote right here. There, right? Vertical asymptote, horizontal asymptote. Limit law, right? Limit law. We've done that. And I just can't help it. I just have to do it now for you. Okay. So limit law. We bring these two together. Doesn't move. Wait. I'm going to bring these two together with limit law. Okay, let me do this. Cut, and paste. Okay, this is a PowerPoint after all. So paste. There we go. Limit laws are together. You see limit laws are together, right? And so that's what I recommend you guys to do. Some of the cards, they're repeats. I just realized there's some repeats. If they're repeats, just remove them, right? Remove them. So let's look at more, right? So horizontal asymptote and vertical asymptotes are discussed. So we have examples, and number 6 is continue the question, right? X to the power 4, sine x, tangent x, arctan, e to the power x, y equals ln x, 1 over x, y equals square root of x, right? All of these functions, which of the following curve have vertical asymptotes? Which have horizontal asymptotes? These are all basic functions, right? So let's just take a quick review about these functions and their asymptotes. Okay, so squeeze theorem. So number 5, right? So we put we done that, right? Number 6, and y equals to x to the power 4. This function does not have any vertical asymptote nor horizontal asymptote. Okay. If we have vertical asymptote, typically we're going to have a point that, first of all, that point function is not defined. What y equals x to the power 4 is defined everywhere. Sine has neither. Okay, so this function y equals to x to the power 4, right? It has no vertical asymptote, nor horizontal asymptote. Okay, has neither. Sine y equals sine x has no vertical nor horizontal. You can, if you have a graphing calculator, you can use a graphing calculator to graph them, or you can use decimal if you don't have those tools. And for tangent x has lots of vertical asymptote, has no horizontal asymptote. And all you have to do is just look at the domain, right? You look at the domain. The domain of tangent is, and of course, if you like to see it and see how and why, sine x over cosine x, right? Whenever cosine x equals 0, that's where tangent is not defined. So what value will make cosine x equal 0? Well, those are, x cannot be, so that's a domain, odd number multiples of pi over 2. Pi over 2. Okay, guess what? The vertical asymptotes for tangent, where we have plenty, we have infinite. Vertical asymptote for tangent would be x equals to any odd number multiples of pi over 2. As you can see the picture, just tangent curve, you should be very familiar with that curve. Okay, so tangent x, you can easily just graph it, right? So all those vertical asymptotes, right, at negative pi over 2, positive pi over 2, 3 pi over 2, and so on and so forth. And those are the vertical asymptotes. Okay, so let's not spend too much time here. If you have any questions, please don't hesitate to reach out to me. Okay, arctangent. Okay, arctangent. Arctangent has 2 horizontal asymptotes. Okay, has 2 horizontal asymptotes. Okay, 2 horizontal asymptotes, and of course, the domain of arctangent is all real numbers, right? The horizontal asymptote, it has 2 horizontal asymptotes. The horizontal asymptotes are, they're plural, are y equals to plus pi over 2 or minus pi over 2. Right? There's 2 of them. Okay, e. Okay, e. E to the power x. Y equals to e to the power x. Right? We're pretty familiar with this function. If you don't, please look at, find the lecture in week 1 where I talk about it, or any resources you can get your hands on studying the function e. Okay, so this function has a horizontal asymptote. That horizontal asymptote is, what is it? Do you know? You may like to pause to write down your answer. The horizontal asymptote actually is this line. Okay, so I'm going to put a broken line, medium. Okay, the horizontal asymptote here is y equals to 0. That's the horizontal asymptote for e to the power x. Okay, horizontal asymptote. Okay, ln x, y equals to ln x. ln x has a vertical asymptote. This is the curve of ln x. If you want to review more about it, I have lesson in week 1. Okay, just look for those titles. And here there's a vertical asymptote, right? Here, there's a vertical asymptote. What is a vertical asymptote? Obviously, that is the y-axis asymptote. Wait, did I spell it right? ASYM, sorry. Okay, that asymptote is x equals 0, right? That vertical asymptote. So vertical asymptote is always x equals something. Horizontal asymptote is always y equals something, okay? Now, we done ln x. Let's look at y equals to 1 over x. Okay, the output is a reciprocal of input. And this function actually, surprisingly, show up in your calculus classes very, very often. Very, very often. Even in the most unlikely place. Okay, it shows up. And how about this one? This one has 2 asymptotes. One is vertical, one is horizontal. Okay, one is vertical and one is horizontal. Okay, so first I'm going to draw this vertical asymptote. Okay, medium. It's a broken one. And there's a vertical there's a horizontal asymptote, there's a vertical asymptote. The vertical asymptote is this. Okay, so it's a vertical asymptote. I make them the same color, but one is vertical, one is horizontal. And what are their equations? Okay, you may like to pause the recording at this moment to write down your answers. So here, I'm just going to copy and paste these words: vertical asymptote, horizontal asymptote, and what they are. Okay, the vertical asymptote is x equals 0, which is the y-axis. The horizontal asymptote is y equals 0, which is the x-axis. Last but not least, on number 6 is this other function y equals to square root of x. This function does not have any asymptote. Okay, this function has no vertical asymptote nor horizontal asymptote. Okay, no vertical asymptote nor horizontal asymptote. Now, number 7. What does it mean for f to be continuous at a? You need to know the definition of a, the continuous function, right? That's 3 points, right? So you want to make sure you understand that. What does it mean for f to be continuous on the interval? Right? It means that you can say about the graph as such a function. And it was for continuous in an interval from -infinity to +infinity. That means the function is continuous in every point at every real number. Okay, so continuous definition of continuous function we are pretty familiar with, right? So where's that definition? It's coming up right here, right? The definition is right here. So that's number 7. Number 9, what does the intermediate value theorem say? Intermediate value theorem, what does it say? Right? It says something about a continuous function on a closed interval. Okay, a continuous function on a closed interval. Intermediate value theorem, and it's a corollary. So these two, they're both called intermediate value theorem. And in our lesson, okay, in my previous recorded lessons, I have talked about how to apply intermediate value theorem multiple times. Let me just show you where to find them. Here we go. Intermediate value theorem, the application of these intermediate value theorem. There's one case I talk about that the interval is given. There's another case, excuse me, the interval is not given and you have to figure out. So these two cases, please study them, and they're both studied and discussed in these recorded lessons. Okay, so keep going. Keep going. Now, intermediate value theorem. Number 10. Number 10. Okay. Oops. Number 10. Write an expression for the slope of tangent line to the curve y equals f of x at the point a, comma, f of a. Okay, for the slope of tangent line to the curve. So how do we do that? Well, this is certainly related to the latter sections, right? Suppose the slope. Okay, so m is the slope of the tangent line. Okay, and the line equation will be y minus f of a, because we're given a point, right? F of a equals to m multiply x minus a. In the case, right, if the derivative exists, if that exists, right, then slope is the derivative of the function at a, right? And then the tangent line equation would be, this will be the tangent line equation, and this will be substituted by its derivative of the function at a. Okay. And of course, you need to know the definition. Number 13. Number 13. I'm just calling because I skipped some questions. I skipped some questions from the textbook. That's number 10. Sorry, this should be called number 10, right? Sorry about that. Number 9. I didn't say anything. Number 9. Number 9. We mentioned number 9. I just didn't write anything down. You heard it. Okay. Define the derivative. Define the derivative, right? So number 13. Derivative, the definition of derivative, there are two versions. There are two versions. Okay, derivative. The version we're going to use, this one and next one. So these are the two different versions. And what does it mean for f to be differentiable at a? Well, definition, right? Either one means the limit exists, right? What is the relation between differentiability and the continuity of function? That's interesting. We talk about it in class. What's the relationship between limit and differentiability and the continuity? Okay, so that's number 15. Well, there's a very important theorem. Okay. Where's my, yes, there's a very important theorem in this part. Okay, it's actually the last part. If f is differentiable at a, then f is continuous at a. This is very, very important theorem. What does that mean? That means if the derivative exists at a, then f is continuous. Okay, f is continuous. So if f is continuous at a, I'm sorry, if f is differentiable at a, then f is continuous at a. So this is guaranteed by theorem. This is guaranteed by theorem. Okay. In another lesson, I talked about the relationship between limit and continuity. Okay. Now, if you look at limit and continuity, you bring these three things together, right? If you bring these things, three things together, there was a lesson I talked about before, which is on. I'm going to go back. Okay, I'm going to go back. I'm going to find that title for you for that lesson. Limit and continuity. Okay, in this lesson, I elaborated about the relationship between continuity. But to summarize, of course, in that lesson, there's a lot of examples illustrated, right? But to summarize, right? If f is continuous, at a, then f has a limit at a. Okay, so these are guaranteed by theorems. These are guaranteed by theorems. Okay, what does that mean? Okay, it means that differentiability okay, so I'm going to put three categories. Differentiability at a implies this arrow means implies continuity at a. Okay, continuity at a. C-O-N, sorry, continuity at a. Continuity a implies limit at a. Okay, differentiability at a implies continuity at a. Continuity at a implies limit at a. In other words, differentiability guarantees limit at a. Okay, so differentiability guarantees the latter two. All right, and the arrow will be reversed. The answer is no. In each case, we have plenty of examples. In the lesson, I just mentioned limit and continuity. I've given examples about if a limit exists, doesn't guarantee continuity. And if continuity exists, right, it cannot guarantee differentiability. And which function is powerful enough to illustrate that? This is the function that is very powerful to illustrate that, okay, this function, okay, is continuous at 0, but it is not differentiable. We talk about this example in class, differentiable at 0. Okay, so continuity does not guarantee differentiability, but differentiability guarantees continuity and limit. Okay, so that's in summary. I think that's the last question on concept. Okay, that's a size. So that discusses what is the relation between differentiability and the continuity of a function, right? So we discussed that, but don't ignore the other lesson I made earlier on, is that the relationship between limit and continuity. So all three major concepts, okay, by this time of midterm, the relationship is completely clear. Okay, and you have, when you study your homework, your other examples, you must make sure you are clear about these concepts. Okay, sometimes it may bring surprisingly simple illustration for you. C, sketch the graph of function that is continuous but not differentiable at 2. Well, for that one, I think you can totally use this function. Okay, you can totally use a tweak of this function, which is the absolute value of x minus 2, that it would do the job. It would do the job. Okay, but what you need to do, well, we covered this in class. Sorry, we covered these in class as how to prove it's continuous, right? We demonstrate it's not differentiable. Now for this function, can you prove that this function is continuous at 2? But not differentiable at 2. Okay, and the proof will be similar. You can find the proof in the textbook. I think in any version. Okay, the proof of the proof of that. Okay, so this proof, okay, continuous at 0 but not differentiable at 0, you can find probably from any textbook. But can you prove similarly that this function f of x equals x minus 2, okay, let me phrase it properly. Can you prove that this function is continuous at 2 but not differentiable at 2? Right? So I leave that for you. I thought you can do it. If you need help, let me know. And I think this is how long I make this lesson. I hope it's not too long. Thank you for watching.